4 is related rates, which is a big calculus, I don't know, hot topic. Okay, related rates, big thing in calculus. What you notice on page 228 is we have introduction to related rates. So technically, related rate starts on the next page. But we've got kind of this introduction page where we're going to work on some of the skills we need to do related rates problems. Okay? So, we are working on, okay, how do we put this in, kind of what we've already been doing a little bit, but how do we take it out of words and put it into calculus notation? Okay, so on these top 4, we're being asked to translate to calculus notation. So the volume of a cylinder is increasing at a rate of 6 cubic feet per second. Thoughts?
Rate is prime, isn't it?
Mm-hmm.
I know that now. I got that wrong on my test.
Okay, so when we see a rate, we know we need to talk about the derivative. What are we talking about the derivative of? The volume. So we're going to do the rate of the volume. Okay. It is increasing, which means that my answer is going to be positive. And it's at a rate of 6 cubic feet per second. So when we write this, we talked about derivative of volume, right? But we're not going to write it as V prime. We're going to go back to the fractions, where we're going to say dV over, what are we taking the derivative of volume with respect to? Seconds, which is time. So, which, when we do related rates, it's almost always in respect to time. Okay, so the volume of a cylinder is increasing at a rate, so dV dt equals 6 cubic feet per second is feet cubed per second. And it's cubic feet per second because it's volume, right? So this is saying the change in volume per time. Change in volume in relation to change of time. That's all we're being asked to do on number 1. But understanding how to write that is important for going into lesson 4. Questions on that? In my brain, that's basic, but that's my calculus brain, so that's why I have to tell me if I need to explain something. Okay, so let's try these others. The depth of water in a rectangular pool is decreasing at a rate of 2 inches per hour. Depth of water. Come up with another word for depth of water. We don't want to talk about volume because depth is a measurement. It isn't a height. Now, am I saying that we couldn't do DD? No, because occasionally it does come up, and I always feel weird saying that, but like as in the derivative of depth.
Oh, okay.
So,
That would
okay.
be awkward to have on
Exactly. So that's why we usually use height. Okay, so the depth of water in a rectangular pool is decreasing at a rate of 2 inches per hour. So what else you got here?
dH over dt equals -2 inches.
That was impressive, guys.
Are we with this? It's the depth of water, and it's decreasing, thus the negative, at a rate. That's our clue. We're talking derivative here. 2 inches per hour. And so that also per hour gives me an idea that it is in respect to time.
Have to remember the negative.
Huh?
Have to remember the negative.
Yeah,
I didn't put a negative on mine.
you weren't the only one.
I didn't either.
I was to say, there were a couple of people that left off a negative.
I put a negative.
The problem is I thought I did everything that was like I did.
Okay, at rush hour, the number of vehicles going through the SunPass toll booth is increasing at a rate of 85 vehicles per hour.
I put DC for D.
But it doesn't say cars.
dV. DV
I don't know. And here's the deal. Is there a right versus wrong specific variable?
No.
There's
we
not.
did it for volume and it
I know. I was going to use V for vehicles. And here's the deal. Again, it's not a right versus wrong thing. It's what's traditionally done here. Okay, so what are you going to tell me?
dp over dt
Okay.
DV
equals 85 d
DT.
per hour.
Oh, you're right.
I don't know. I don't have a good abbreviation for vehicles, so. Okay. 4. Air is escaping from a spherical balloon at the rate of 15 cubic centimeters per second.
Rate decreasing.
It's not volume.
Escaping is decreasing, so it'll be negative. Thanks, Queen.
Okay. I heard some talk about what this is. We're talking about air in a balloon.
I'm
Yes.
I'm still thinking.
And here's my hint.
Volume.
Oh,
I see
wait,
cubic.
sorry.
I was.
I'm going to say volume. Okay. And I heard some talk about volume, but I heard like some negative talk about volume, like that's not right. So, yeah.
dp over dt.
I swear.
So this is air is escaping from a spherical balloon. So this is the change in volume with respect to time. It's escaping, so this balloon is getting smaller, so negative 15
Centimeters cubed per second.
cubic centimeters per second. Okay. You getting the idea? Because we have to be able to write these types of things and understand this types of calculus language to do related rates problems. Okay? Okay. Moving to the bottom part then. In the formulas below, take the derivative with respect to time. Remember to consider which variables change with respect to time before you take the derivative. So, kind of think the word has escaped me. Yeah, and so area of a rectangle. Oh my gosh. This is not all in one variable, right? So this is not like it's solved y equals, and then everything's in terms of x. So what is the word for the type of differentiation I want to use?
Implicit.
Implicit, thank you. I cannot come up with it. I don't know, my brain's not there. But we want to think implicit differentiation here, okay? So when we talk about taking the derivative with respect to time, okay? So that means when I say, okay, the derivative of area, we're going to say, I'm going to use the a dt. Okay. Now, how do we take the derivative of the right side there?
Them being multiplied.
L prime.
Product rule.
Thank you.
Oh yeah, that's a good one.
My brain thought multiplication.
So you're starting like me. You can't come up with the word, but you know what you're thinking. You can't come up with the
That's
word.
a lot of product rule on that.
Okay. It's not all product rule. Okay. Now, when we look at this, okay, take the derivative of one, keep the other, and then flip it, right? So in this case, what do you want to do?
L prime W. L prime W.
Okay. Except I'm not going to use primes here. Okay. I'm going to use with respect to t, right? Okay, so the derivative of L is 1 and then times dl dt, and then we're keeping the w, right? So I'm actually writing this as w times dl dt. Product rule says we add. And now this time,
L times dw dt.
we're going to keep the L, and the derivative of W is 1, and then dw dt. Okay? So, whenever, it's very much like implicit differentiation, where you're taking that derivative with respect to time, it is like saying an L times an L prime or a W prime, except we express it as the dl dt and the dw dt.
That's crazy that there's not a single number in that math.
Not anymore.
Okay.
I'm having
Hey, there will be numbers in related rates. I will say that.
Hey,
Okay, circumference. Okay, let's take the derivative of circumference.
DCT.
Okay? The derivative of circumference with respect to time, so dc dt. I disagree.
Well, we only have two product rules
Yeah.
because
No.
one product rule because 2 pi is a constant. No, r is
So it's just
constant.
R.
It's 2 pi.
So let me ask this. If you had to do the derivative, hold on. You guys are way overthinking this. If I asked you what's the derivative of 2x, what are you going to say?
2.
So what's the derivative of 2 pi x?
2 pi. That's what I was saying.
Yeah.
So what's the derivative of 2 pi r?
2 pi.
2 pi. In other words, 2 pi,
Bang my head against the wall.
okay, 2 pi is just like 2 is a constant, pi is a constant. So we don't have to do a product rule unless there are two things to take derivatives, unless there are two variables.
Yeah.
Okay? There's not two variables, there's not two functions happening. It's just an r with numbers in front of it. Okay? So this is, subtract 1 from the variable, multiply it out front, that type of thing. So, okay, so what is the derivative of 2 pi r then? 2 pi
dr dx. Oh, dt.
dr dt. Everything is with respect to t today.
It says it in the instructions.
Okay? So derivative of 2 pi r is 2 pi times the derivative of r with respect to time. Okay? Let's try volume of a cube. Derivative of volume of a cube.
3s squared.
Derivative of volume with respect to time, dv dt. Derivative of s cubed is
3s squared.
3s squared times ds dt.
There's
Well, there was a
Okay.
2 in the last one.
Okay. Lateral surface area of a cylinder.
good
I don't remember.
No, it's still 2 pi. Because 2 pi r is one thing. And
And then you have to do the product rule.
Okay. And by the way, folks, you can't do multiple product. I mean, it's one times the other. There's not like a product rule for 3 things multiplied. Okay. So, if we think of this as 2 pi RH, or here's another option.
Are we going to do the chain rule?
I'm just thinking of this, and maybe I shouldn't put that there, but the idea of kind of factor out the 2 pi out front so we don't have it in each term. Or maybe we should just do it in each term and then I'll factor it out.
why would it be in each term if it's just 2 pi r?
Because
Okay, hold on. Okay, let's go through this. Forget I said anything about taking the 2 pi out. Let's just go through this.
You'll see.
Okay, so derivative of s,
DS over DT.
ds dt, is equal to, okay, so if we're doing our product rule, it's 2 pi r times h. What's the derivative of 2 pi r?
2 pi
Times
dr
dt.
2 pi dr dt, and don't forget they're still in
H.
h. So I'm going to say 2 pi h
dr dt.
dr dt. It's all the same pieces, I just changed the order, right? And then plus, and now
2 pi r.
2 pi r.
2 pi r stays.
DH.
The derivative of h is going to be 1 and then times
You see what it
dh dt. So now,
Yeah, 'cause it's just
2 pi ends up in both terms.
So you
So
Then you factor it out.
what you can what I was saying that we could have done is we could have just put the 2 pi out front and then just done the product rule with r times h. That's what I was trying to say was an option, but it wasn't going to fly, so I just backed off. But so the 2 pi factors out, h times dr dt plus r times dh dt. They are equivalent statements that you can talk about there. Okay? Okay, 9. Area of a circle. Change of area with respect to time, dA dt, equals
2 pi r.
Okay.
dr.
2 pi r dr dt. Are we getting okay with these?
Yeah.
Okay. Perimeter of a square.
dp dt equals 4ds
dp dt, the change in perimeter with respect to time, is equal to what?
4 ds
DSDT.
Derivative of 4s is 4 times the derivative of s. And technically we are doing chain rule on all of these because that's what this ds dt is. It's the chain rule. Derivative of 4s is 4 times the derivative of s, which is ds dt. Okay? Volume of a cylinder.
Now let's take the pi out.
Okay, so kind of like this one up here. We could take the pi and just put it out front and put the whole rest of the thing in parentheses. Okay, and so if that's the case, what we're doing is we're thinking of this as pi times r squared h. And so the pi is just a constant, it just stays out front, and we're just doing the derivative of the r squared h. Okay? Let me see, yeah. Okay, so dv dt, if I just put the pi out front. Okay, so now what are we doing there?
2r dr dt.
Derivative of r squared is 2r times the derivative of r is dr dt times h, because we got to keep the h. And then
Plus
plus, this time we're going to
r squared.
keep r squared. The derivative of h is
1 dHdt.
1 dh dt. Okay.
Wow.
Could you also have that pi multiplied in? You
Yeah.
could. I have an or written in my,
Doing all that.
I was like, yeah, I have an or written in here as 2 pi RH dr dt plus pi r squared dh dt. Okay, and neither's more right than the other. I think it is definitely a benefit if you can understand that they are equal and recognize that fact. Okay. Ready for 12? Okay. dv dt
Times h dr dt.
Okay, so if we keep the 1/3 in here, is that what we're doing at this point? Okay, and it's an option, right? If you keep the 2/3 or the 1/3 in there, when you multiply by 2, right, it becomes 2/3 pi r. Keep the h and then times the dr dt plus keeping 1/3 pi r squared. Derivative of h is going to become dh dt. Okay? Now, with this in mind, the other option that you could have done is you could have pulled the 1/3 pi out front.
That's what I.
If I pull the 1/3 pi out front, realize in a calc text, you would likely see it written as pi over 3. Right? And so then you would have still had the 2 pi r h dr dt and r squared
You wouldn't have the pi in there, would you?
dh dt. No. I'm not rewriting all that. Nope, thank you. Okay. Okay, did you already do volume of a sphere?
That's
dVdt
yes.
equals
4 pi
4 pi r
squared
squared
dr
dt.
Say it again slower for people in the back.
Do it on your own.
You got it. Ken.
Think it.
You got it.
We can do this.
Don't worry about what they say.
I'm not looking at 14.
Okay. Okay.
Yeah.
4/3 pi is just a constant, right?
Yep.
So multiply the 3 out front. 3 times 4/3 is 4 pi r squared times dr dt.
That one on the other hand looks like that.
14? No. Just think implicit differentiation.
You can say words.
Okay. You know implicit differentiation. Your brain's just
I
not.
know what it is, but I.
Okay, so the difference here on each of these, we've just been taking the derivative of each piece with respect to time. And that's what we're doing here, okay? What's the derivative of x squared?
2x.
2x.
dy dx. d
DX.
dx dy. dt.
Still with respect to time today. We took the derivative of an x variable with respect to time.
dy dt.
dy
Listen,
dt
I'm trying.
equals 0.
Why?
You guys are being rough on each other. Okay,
I thought you would think
so 2x dx dt plus 2y dy dt equals 0. Huh? So there's not, so this is like a Pythagorean theorem problem. Okay. I have written in my notes when we start talking about a ladder sliding down a wall. Okay. I have sliding ladder problems reference here. So like this is a common setup you would see in a sliding ladders problem. Okay.
you don't need the D something over T. Do you?
Okay. Okay, guys. This is trying to get us into the idea of how to write this material. Okay? Okay. As we look
I don't like
at the first page, we got some reading to do here. Okay? The derivative dy dx of a function that is like an f of x function is its instantaneous rate of change. Okay? So we're talking IROC here with respect to the variable x. When a function describes either position or distance, its rate of change is interpreted as velocity. Okay, so what we already know, if the basic function is position, the derivative of position is velocity. In general, a time rate of change answers the question, how fast is a quantity changing? And they give some examples here. So if V is volume that is changing in time, then dV dt is the rate of the volume changing. Okay, so V represents volume, dV dt is the rate that the volume is changing. And we'll talk a lot about that, or how fast the volume is changing with respect to time. If a person is walking towards a street lamp at a constant rate of 3 feet per second, then that distance between the person and the street lamp, that's what's changing. And so the distance is decreasing. So dx dt there. If you were walking away from the lamp, and we're talking about distance from the lamp, then the distance is increasing and the rate of change becomes positive. all kind of stuff we know a little bit, but we're going to really work with it more and put it into play. Now, this says guidelines for solving related problems, okay? I'm trying to remember if I label my steps. I don't totally label my steps, but we're going to kind of think about it in terms of steps, okay? Step 1, often the suggestion is to make a sketch. Okay, sketch a picture, label any quantities. Okay. She has it set up that we're going to read the problem, identify all quantities as what we know, what's given, and what we have to find. We're going to write 3 is write an equation involving. I can't read, man. Glad you guys can read. I hope. Involving the variables whose rates of change either are given or are to be determined. So you're going to be looking to write an equation that connects our variables. Okay. 4 will be implicit differentiation, which is what we just did on the previous page. Okay, that's what we were just practicing. Is that implicit differentiation? We're always going to be differentiating with respect to time because it's a related rates problem. After completing step 4, substitute into the resulting equation all known values and basically solve at that point. Okay, so this is kind of a set of steps to take you through things. Now, I think example 1 I don't see as much as a traditional related rates problem. I feel like when we get to like example 2, that's more your traditional related rates problem. But this is kind of getting us the idea of the solving steps, I guess. So suppose x and y are both differentiable functions of t and are related by the equation. Thank you. Y equals x squared minus 3x. We're being asked to find dy dt when x is 3, given that dx dt equals 2 when x is 3. Okay, so we were given the equation y equals x squared minus 3x, yes? So with that in mind, we're being asked to find dy dt, right? In order to find dy dt, we have to talk about the derivative with respect to time. So, yeah, when we take this, we're going to take the derivative with respect to time. So, what is the derivative of y?
1 d.
Okay. dy dt. Derivative of x squared.
2x.
She started to slip the y back in there. Minus the derivative of 3x.
3x.
dx.
Are we all good with that?
Yeah.
I feel like we have the basics here. From here, it is basically a plug the information in. Okay, now, we could clean this up a little bit if we wanted to. In that, what do you notice on the right-hand side? Both terms, and I'm not saying you'd have to, but the way we ended up writing it, both terms have a dx dt, yes? So I could write this as 2x minus 3 times the quantity, or the quantity of 2x minus 3 times dx
Can you flip it
dt.
around to where dx dt is in the front?
You can, it's just not traditionally done that way. Okay?
not?
Because dx dt traditionally goes at the back.
What? That's
Not
so
to me.
dumb.
I don't care.
I know, I have it my way.
Now,
I
I
had
said
mine in front.
traditionally. I said it
Mine twisted
traditionally,
though.
yes?
I have it my way.
Okay. So did I say it was wrong?
No.
No. Okay.
We were all about to be really bitter if you did.
I mean,
Okay.
I'll just,
Ugh.
Now, we are being asked to find dy dt. I'm going to use the evaluation bar at x equals 3. We already have an equation solved for dy dt, don't we? Plug the information in. 2x minus 3, so 2 times 3 minus 3. What do we know about dx dt? It equals 2 when x is 3.
What?
it's in
It's
the,
given.
yeah.
Oh.
Given information.
In other words, I'm using the fact that x equals 3, dx dt equals 2. Do some math.
6.
I wouldn't distribute, I would just do the stuff inside. So dy dt, when x equals 3 is equal to 6. I just boxed. I never box in this class.
I underlined, but I prefer box.
No.
I used to box until this class.
I know, I used to box until this class too. I will say I have seen more mixed. I don't know. Some people say don't circle, don't box your answers, because that is your answer and they can't look at anything else on the page. Other people say it's not that cut and dry. It'll depend on the problem. If you box an answer, that's not the end of the world. So
What about like on the AP test?
that's it. I mean, I think what it comes down to is there are situations where if you circle that, box that answer off, circle that answer off. If you're saying this is my answer, it could get you into trouble.
I'm just gonna start a sign right under the answer.
Okay,
Don't do that.
Yeah.
a pebble
You should be copyrighted.
is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, what is the rate? At what rate is the total area of the disturbed water changing?
It's like that. Where do you even get that from?
What is a concentric circle?
Just like a regular circle?
circle.
Oh.
So here's my pebble.
Have you ever seen Orville?
Yeah, but why describe it as a concentric circle?
Mario.
Okay, there's your concentric circles. Not drawn the best, but you get the idea, right?
Good
You
enough.
drop the pebble, and then if you watch the water, there's circles like rippling out.
Yeah.
Okay. So, with that in mind, okay, we've got to figure out what we know, what we need to find, so on and so forth. So, a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. So let's focus on this sentence. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. How would you write that?
Constant rate and increasing is derivative.
Okay. drdt is
Equals.
I have this in the given section. I don't like her no section, I'll be honest, but so because it's talking about the radius is increasing at a constant rate. So because they said rate, we're going to think drdt. And what is that rate? 1 foot per second. That's given, yes? Okay. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? What are we being asked to find? We're being asked to find dA dt when
DRDT. No, not DRDT.
When R
when r equals 4. Okay. When the radius is 4 feet. That's not saying when the change of the radius is 4 feet. That's what it's saying when the radius is 4. So when r is 4, at what rate is the total area changing? So that's your dA dt. Okay. We were given the change in the radius is 1. The no, what she tends to put in the no section, if I recall, yeah. Think formula here. What's going to be our formula that we're going to have to use that connects these variables that has to do with the problem? What's your formula?
Area of the circle.
Yes? We're talking about the radius. We're talking about the area of the circle changing. So what is area of a circle?
The pi squared.
So that's what we know. Okay. So I always like to read through and get down all the information. Okay. We're given, we know what all the numbers were we were given, what we have to find, and what formula we're going to use. So, A equals pi r squared. And I'm not really referring to these steps as I probably should be. Let's see. Make a sketch, label quantities. There wasn't really a sketch to make here other than we talked about concentric circles, right? Okay. Read the problem, identify all quantities. We've done that, right? We read the problem, we went through, identified all quantities. Write an equation involving the variables, which we have. So we're really at step 4. Using the chain rule, implicitly differentiate both sides of the equation with respect to time. We just did this on the previous page. Differentiate for me with respect to time. dA dt equals
2 pi r.
Technically, we have this exact answer on the previous page, don't we?
Yeah.
Awesome.
You could technically go back and steal the answer, but in reality, you need to make sure you know how to do it. Okay, so we have differentiated. Now, at this point, you have an option. And, yeah, okay. Well, we can do this one. Actually, it's already solved for dA dt, isn't it? Because we're going to be solving for dA dt. So at this point, it's plugging in what you know. So we're being asked to find dA dt, yes? 2 is 2. Pi is pi. What did it say about r? When r is 4. You never plug that 4 in originally, because then we don't have an equation to differentiate and work with. So you always wait till you're getting to your answer. So now we're going to plug in 4. What about dr dt?
It equals 1%.
It's 1, yes? Dr dt is 1. So you're going to substitute that 1 in also. Okay, so that step right there is you are, and I'm just going to write this up here in case we need it. I don't know if we need it or not, but we are substituting in r equals 4 and dr dt equals 1. Could you throw the labels in there with them if you wanted to? You could. But I'm not going to worry about it. Maybe I should. Okay. Do the math. What do we get?
What?
Like, how do you not get
Oh, 8 pi.
Sorry.
Oh my god.
Sorry.
Because Sophie and I were just discussing how she doesn't know how to do basic algebra and basic math anymore.
Sophie, did you put 6 by 2?
What?
She said 6 pi out loud, or one of you did. I heard it.
Pi out loud.
I also
Yeah.
said 6 by out loud. I'm like, yeah.
And I'm sitting here thinking, okay.
4 minus 1?
No, I just
No, they did
times
2
the
plus
1,
4.
And then I did 2 plus 4.
Oh, no. I got 3. 4 times 1 is 3. That's what I got.
That's beautiful.
Don't know how, but.
Okay.
Nice.
You guys are
Anywho.
making life rough. Now,
You would know.
officially, I just realized, officially up, I should have probably put in right here at r equals 4, right?
Well,
That's what I had at first.
Sorry.
Then I erased it. You didn't have it.
Sorry. Okay, now, let's talk labels. And this is why maybe I should have gone ahead and put labels in. But this is the, look at what, think about what dA dt is. Change in area over time. So what kind of label does that give me in this problem?
B squared.
for a second.
Because area is units squared, time is seconds in this
You
problem.
do like feet squared slash instead of a fraction mark.
Same thing.
I'm
Don't
just
we?
kidding. I'm just
Okay.
Next problem.
Okay,
Oh, we're underlining again.
Wait, why did you underline it?
That's the end.
it's my final answer. As opposed to boxing, which I slipped up and did the last problem.
Oh.
They're calling me out on it. Okay, example 3.
Yep.
This is basic, guys, okay? This is basic, this is beginner level. We've got to grow from here.
Yeah, I know.
I don't like rotating, and that's the problem.
Okay. Air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute.
Not very colorblind.
How fast is the radius of the balloon changing at the instant the radius is 30 centimeters? Okay. What do we know? What are we finding? What do we, anything?
Well, we know volume of a sphere.
Okay. Let's see. So air being pumped into a spherical balloon means we are talking volume, yes? Huh?
This says cubic centimeters.
Okay. Oh, okay. And so also back to the fact that they gave us a cubic label. So if we're talking about volume, spherical balloon, you have a formula?
dvdt. Oh,
4 pi.
Wrong.
sorry.
You guys, I don't know. Which part do we want to fill in first? Okay.
I just picked 2
I
pi.
knew I would know.
Pi r to the 4th
Isn't it 2 pi?
I don't know.
Volume of a
of sphere.
Oh,
Hey,
not a
guys.
circle.
It's, wait a second. 4 pi r squared.
I'm
And then you were like, 2 pi.
Okay.
It's in here.
But that's not. Okay, wait.
4
Where are you
thirds pi
Okay, so
r.
volume of a sphere. Don't give me the answer to that problem right now, though, Hannah. Give me what is the volume of a sphere?
Oh.
4/3 pi r cubed. Where did she get that from? Page 1 today, right?
Yeah, that's what I just went and looked at.
I know. I forgot that it was there. So 4/3 pi r cubed. That's a good formula to know. Okay, what's given? Think numbers here. What's given?
8 cubic centimeters per.
Radius is 30 centimeters.
Hold on.
Okay.
So.
What about this 800 cubic centimeters per minute? What is that?
dvdt.
Wow, Mario.
That's impressive.
You were waiting.
Okay, air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. So this is the change in volume over time, yes?
Yes, I know.
Okay,
R equals
Why
30
did I
centimeters.
do
now, save that r equals 30 for part of find. Because, okay, notice, and just beware of this.
Because it's at.
Because it's saying, yeah, how fast is the radius of the balloon changing at the instant the radius is 30 centimeters? If you plug 30 in too soon, we're going to have a problem in our hands. Save it for when we're trying to find. So we're trying to find something at 30. What is it we're trying to find?
Pi r.
Volume. Or no,
Wait,
how fast the radius is changing.
How fast the radius is changing. What are we going to call that? We're trying to find dr dt
Evaluated at R equals 30.
when r equals 30.
Good job.
There you go.
Are we there?
Yeah.
Okay. And I can put 30 centimeters if I want. Okay. So, we're ready to start. The formula I'm using, V equals 4/3 pi r cubed. We need to take that formula and differentiate. Derivative of V is dv dt. Derivative of 4/3 pi r cubed,
4 pi r squared drdt.
4 pi r squared dr dt. Now we're ready to,
Plug.
Plug and check.
Evaluate at
okay,
r equals 30.
we're trying to find dr dt. So at this point we're trying to fill in what we know. What do we know?
R is supposed to
R is going to be 30.
And dr. Oh,
dv dt is 800 centimeters cubed.
what?
dv dt is 800.
Oh, dang it.
I put, yeah, I'm moving that way. I'm not getting mine out of my pencil case.
It clearly says
Behind enough
dv
that I can
dt.
understand.
And what are we trying to find?
dr
dr dt. Are we okay with what I just did?
Yes.
I mean, not really, I know, because you're mad at me,
Okay,
but
wait a second.
4 pi r squared dr dt, right?
Mm-hmm. Okay.
But we know R. Oh, you
Plug in
just,
30.
no.
I plug. So at this point, we're at that. Okay, that's fine. So you plug in all the numbers you know. We were given that dVdt is 800. We're at that point. We're trying to find and that's the key. Is you should know everything. You should be able to plug in and fill in everything except drdt at this point. Okay. So 800 is 800. 30 squared is 900 times 4. 3600 pi dr dt. I didn't pick up my calculator yet. Just saying.
That's impressive.
You divide by 3600.
Yeah, I did this differently in my notes. I need to quit looking at my notes. So divide by 3600 pi. Yes.
That's a 1. No, it's not. Yeah.
So dr dt is 800 divided by 3600 pi. My non-calculator brain is going to, first of all, cross out my zeros. So now I have 8 over 36 pi. 8 and 36 both divide by 4.
2 over 9.
2 over 9 pi. Now notice, where is that pi? It is specifically in the
Denominator.
denominator. So,
Because
Denominator.
it was 6.
dr dt is 2 over 9 pi. Give me a label.
Centimeters cubed per minute.
Centimeters.
Does it need the
Per
evaluated
minute.
at R equals 30 still?
No, we already did.
No, so we already valued.
Centimeters.
Well,
Centimeters squared per minute. Right? Because it's radius?
radius is just a unit, a measurement.
Oh, centimeters.
So just centimeters per
Minute.
minute. You could have the evaluated at, usually at the end I don't necessarily. I guess I did on that last one, but I don't necessarily at the end. Okay, are we there?
Mm-hmm.
Okay.
That makes me think of DMS.
What's that?
Degrees, minutes, seconds.
Tomorrow we'll talk about a sliding ladder. We'll talk about a ship sailing.
Lamppost.
We'll talk about a cylinder. We'll talk about a cone, a leaking cone. We'll talk about a lamp post. Hopefully if time allows for all of this. Okay,